KitKat, Ferrero, and Hershey's are engineered in unbelievable high-speed candy factories built to feed the world's sweet tooth. From massive mixers to precise layering machines and rapid-fire packaging lines, each brand runs like a sugar-fueled powerhouse. In this video, we take you deep inside the chocolate-making process behind these iconic treats to showcase their impeccable efficiency. A crisp snap, a creamy melt, and a perfect balance of chocolate and wafer. KitKat is more than a candy bar. It's a confectionery icon, loved worldwide and instantly recognizable for its 4 slender fingers and clever tagline. KitKat stands as a shining example of how precision engineering, food chemistry, and high-speed automation can come together to craft something remarkably simple and yet technically intricate. To understand how KitKat is made in a factory, we have to start with its dual nature: half chocolate, half wafer. Each must be manufactured independently with extreme care, then combined at the right moment to create a product that tastes the same, whether it's made in Japan, the UK, or Canada. The process begins with the preparation of raw ingredients, and the base of it all is wheat flour, used for the crispy wafers. This flour is stored in towering silos, aerated and filtered to remove dust and contaminants. It's pneumatically conveyed to the mixing room, where it's combined with sugar, palm or sunflower oil, milk powder, salt, baking powder, and water. These ingredients are deposited into large, jacketed horizontal mixers, which knead them into a consistent, homogeneous dough. At this stage, automation systems monitor dough temperature and hydration levels, adjusting mixer speed and timing accordingly. Once the dough is ready, it's extruded into thin sheets. This happens on massive wafer sheet lines, flat conveyor belts, where rollers press the dough into sheets less than 2 millimeters thick. These sheets move through high-capacity baking ovens that use convection heat to evenly cook them. These ovens stretch over 50 feet long, operating at temperatures around 180–200 degrees. Each wafer sheet bakes for less than 2 minutes, but emerges dry, crisp, and golden, ready for layering. Now comes one of the most signature features of the KitKat: the layered wafer structure. Each wafer sheet is passed through a slathering station, where a precise amount of wafer cream, a chocolatey, fat-based paste, is applied to its surface. This cream, made from finely ground sugar, fats, milk solids, and cocoa powder, serves as both flavor and adhesive. Multiple layers of wafers and cream are stacked, typically 3 wafers and 2 cream layers, forming a block known internally as a wafer book. These wafer books are pressed under light pressure and sent through cooling tunnels to stabilize the cream. Once firm, they are sliced into individual fingers using ultra-sharp guillotine blades or water jet cutters. Each finger is a perfect rectangle, dimensionally identical to ensure they fit precisely into the chocolate molds in the next stage. Meanwhile, chocolate production is running in parallel. KitKat uses milk chocolate, which must be refined and tempered to perfection. The chocolate begins with cocoa liquor, cocoa butter, milk powder, and sugar, all blended together in mixing tanks. From there, the mixture is passed through refiners, a series of large rollers that crush and flatten the mixture into particles smaller than 20 microns. This size is critical to achieving the smooth mouthfeel expected of high-quality chocolate. After refining, the mix enters conching machines, giant heated vats where the chocolate is stirred, aerated, and aged for several hours. This removes bitter volatiles, improves texture, and develops flavor. Once conching is complete, the chocolate is tempered, a precise process of heating, cooling, and reheating the chocolate to promote the formation of stable cocoa butter crystals. Without this step, the chocolate would be dull, soft, or prone to blooming. Tempered chocolate has a shiny finish, satisfying snap, and melt-in-your-mouth consistency. Now the chocolate and wafer fingers are ready to unite. This happens on a molding line. First, plastic or stainless steel molds are warmed slightly and filled with a thin layer of tempered chocolate. This bottom layer forms the base of the KitKat. Then, the pre-cut wafer fingers are robotically placed onto the chocolate-filled molds. Another dose of chocolate is deposited over the top, fully enrobing the wafer fingers and completing the bar structure. The filled molds pass through a vibration table to remove air bubbles and ensure complete coverage. From there, they travel through a cooling tunnel, a refrigerated chamber where the chocolate crystallizes and solidifies. By the time the molds exit, the KitKat bars are fully formed, firm, and ready to be demolded. Demolding is fully automated. Each mold is flipped, and a gentle mechanical tap releases the bars onto conveyor belts. The now empty molds are cleaned, sterilized, and recirculated back into the system. The KitKat bars now move to quality inspection. Vision systems equipped with high-speed cameras scan every bar for size accuracy, surface defects, cracks, or incomplete coatings. If anything is off-spec, that bar is removed from the line. Approved bars continue on toward the flow wrapping station. Packaging is a crucial part of the KitKat experience, not just for branding, but also for shelf life. Each bar is wrapped in metallized plastic film that acts as a barrier to light, oxygen, and moisture. The flow wrappers operate continuously. Bars are fed onto belts, aligned by guide rails, and pushed through a forming collar where the film is wrapped around them and sealed with heat-sealing jaws. Wrapped bars are then grouped into multi-packs or secondary trays, depending on customer requirements. Robotic arms or pick-and-place machines assemble the bars into display-ready formats. These units are then placed onto pallets using automated palletizers and stretch-wrapped for transport. Every step of this process is monitored by SCADA systems and connected sensors. Mixing temperatures, dough moisture, oven humidity, chocolate viscosity, flow speeds, and packaging integrity are all logged in real time. If a parameter drifts outside the set range, alerts are triggered and corrective action is taken immediately, either by automatic control or operator intervention. Meanwhile, samples from every production lot are pulled and sent to the on-site quality assurance lab. Here, technicians run texture analysis, moisture content testing, shelf stability trials, and most importantly, sensory evaluations. Trained tasters assess whether the product matches the official profile: crisp but not dry, sweet but not cloying, and a melt that delivers the cocoa hit right before the wafer crunch. Beyond quality, KitKat factories are also designed with hygiene and allergen safety in mind. Separate lines may be maintained for peanut-free or gluten-free variations, and full allergen switchover protocols are implemented if recipes change. Stainless steel surfaces, clean-in-place systems, air filtration, and pressure-zoned rooms ensure that each environment is sanitary and safe. Sustainability is also an emerging pillar of KitKat's production. Many factories now source Rainforest Alliance certified cocoa, and water and energy recovery systems are implemented to reduce waste. Chocolate scraps and wafer trim are collected and reprocessed, either reused in internal production or recycled into other food streams. From raw wheat and cocoa beans to precision molded chocolate fingers, the production of KitKat is a dance of science and craftsmanship. It's easy to take for granted, something you grab at the store, tear open, and snap into without a second thought. But behind every bar is an extraordinary feat of coordination, timing, and innovation. It's the result of countless variables, all controlled within narrow limits, to ensure that when you have a break, you're rewarded with the exact flavor, texture, and snap you expect. Golden foil, delicate layers, creamy filling, and a whole hazelnut at the core. Ferrero Rocher is the epitome of premium chocolate craftsmanship. But what seems like a luxurious, handcrafted treat is actually the result of one of the most precise and sophisticated chocolate manufacturing operations in the world. Produced by the Italian confectionery giant Ferrero Group, Ferrero Rocher is a marvel of layered architecture and synchronized automation. And to truly understand how it's made, we must step inside the walls of one of their advanced, high-security confectionery plants. It all begins with the hazelnut, Ferrero's signature ingredient. The company is one of the largest consumers of hazelnuts globally and maintains close relationships with farmers across Turkey, Italy, and Chile. Only whole, uniform, high-grade hazelnuts are accepted for use in Ferrero Rocher. Upon arrival at the processing facility, the hazelnuts are cleaned to remove debris, shelled, and subjected to multiple rounds of size grading and visual inspection, both by machine and by human eyes. The hazelnuts are then gently roasted in continuous drum roasters. These large, rotating cylinders apply indirect heat to evenly roast the nuts without scorching them. Temperature and time are tightly controlled, typically around 150-160 degrees Celsius for 15 to 20 minutes. The goal is to enhance the nut's natural oils and flavor without damaging the internal structure. Once roasted, the nuts are cooled rapidly to halt the cooking process, then transferred to storage under nitrogen to preserve freshness. With the hazelnuts ready, attention turns to the wafer shell, the crisp, spherical layer that surrounds each nut. The wafer is made from a batter of wheat flour, water, sugar, oil, and leavening agents. The batter is deposited onto heated hemispherical molds in automated wafer baking machines. These molds close like clamshells, sealing and cooking the wafer until it forms a hollow, thin sphere. This process takes only seconds, and each wafer shell is then cooled, trimmed, and conveyed to the filling station. Now we move to the cream filling. This smooth, chocolate hazelnut cream is made using a proprietary blend of ingredients: cocoa, milk powder, sugar, and hazelnut paste. The hazelnut paste is prepared by finely grinding roasted hazelnuts into a silky nut butter, then blending it with cocoa solids, vegetable oils, and emulsifiers. The mixture is heated, homogenized, and passed through conching units to develop a smooth texture and balanced flavor. At this point, multiple streams converge. A whole roasted hazelnut is placed in the center of each wafer hemisphere. Then, a precise amount of the chocolate hazelnut cream is deposited into the cavity, encasing the nut. The wafer sphere is closed by joining two halves together with a light pressure and a ring of filling acting as an adhesive. Each filled wafer is now a complete, delicate core, ready for the outer coating. The first coating is a layer of milk chocolate. The filled wafers travel along a conveyor through a curtain of tempered chocolate, a process called enrobing. The chocolate is kept at exact temperatures to ensure optimal viscosity and crystallization. Too hot, and it will be too thin and won't set properly. Too cold, and it will be too thick or bloom later on the shelf. The enrobing tunnel applies a uniform coat of chocolate that covers the wafer sphere entirely. Immediately following enrobing, the still wet chocolate is dusted with finely chopped, roasted hazelnut fragments. This is done through a synchronized nut dispenser that sprinkles fragments over the rotating, chocolate-covered spheres. The particles adhere instantly to the tacky surface, forming the crunchy outer texture that defines the Ferrero Rocher bite. From there, the products enter a refrigerated cooling tunnel to crystallize and harden the chocolate coating. This tunnel is kept at a consistent low temperature, typically around 10 to 12 degrees, with humidity controls to ensure shine and stability. Once fully cooled and set, the Ferrero Rochers pass through a final inspection system. High-speed vision cameras scan each sphere for cracks, missing nut fragments, or uneven coatings. Those that fail to meet visual standards are removed automatically by pneumatic diverters. The acceptable pieces then move into one of the most iconic parts of the process: foil wrapping. Ferrero's wrapping process is instantly recognizable. Each sphere is wrapped in a piece of gold foil, folded tightly by high-speed rotary wrapping machines that spin the foil around the product in a process similar to a ballet. The wrapping must be secure but not crumpled, an art that's perfected through decades of machine design and precision calibration. A paper band with the Ferrero Rocher logo is heat-glued around the equator of the foil, acting both as branding and as a seal of authenticity. Wrapped Rochers are then gently placed into brown fluted paper cups, which not only help with presentation, but also protect the spheres from scuffing. Robotic pick-and-place arms transfer the wrapped products into their cups and arrange them into trays or gift boxes. These boxes may contain 3, 12, 24, or even 48 pieces, depending on market and seasonal packaging. Secondary packaging lines group the gift boxes into cartons for shipping. These cartons are automatically assembled, packed, and sealed using robotic case packers. Once completed, the cartons are barcoded, weighed, and stacked onto pallets by robotic palletizers, then stretch wrapped and scanned into inventory. From here, they enter climate-controlled storage warehouses, awaiting shipment to distribution centers around the world. Of course, quality control is continuous throughout the entire process. Every batch of cream filling is lab tested for fat content, viscosity, microbial load, and texture. Wafer shells are tested for brittleness and moisture content. Chocolate is sampled for bloom potential, fat migration, and melting point accuracy. Finished products are subjected to sensory panels who evaluate every aspect of the bite, from crunch to melt to aftertaste. Behind all of this is a digital infrastructure that ties everything together. From syrup cookers to nut roasters to packaging robots, the plant is run by integrated SCADA and MES systems. These systems monitor temperature trends, downtime events, ingredient usage, and traceability data in real time. Each product can be traced back to its lot of hazelnuts, batch of chocolate, and shift team, allowing full accountability and rapid response in case of any deviation. What's more, Ferrero production plants place a strong emphasis on food safety. They are certified to international standards such as ISO 22000 and FSSC 22000, and operate with strict allergen segregation, hygiene zoning, and air filtration systems. Operators wear full protective gear, and certain areas are restricted to minimal human presence to reduce risk of contamination. Sustainability has also become a central pillar of Ferrero's operations. The company has invested heavily in traceable and responsibly sourced hazelnuts and cocoa. Many factories are now equipped with heat recovery systems, water recycling units, and energy-efficient machinery to reduce the environmental impact of confectionery manufacturing. Incredibly, this entire process, from nut to wrapped product, can happen in under 2 hours. That's 2 hours to roast, fill, coat, wrap, and package what looks like a handmade luxury. But it's not magic. It's manufacturing at its most precise. Every movement of every machine, every gram of chocolate, every foil fold is measured, managed, and monitored. The result is consistency across countries and climates. A Ferrero Rocher purchased in Rome will taste the same as one bought in Dubai, Tokyo, or Toronto. That uniformity is achieved not through simplicity, but through complex synchronization across ingredients, machines, and human craftsmanship. From a distance, Ferrero Rocher production might seem effortless, but it's anything but. It's a feat of edible architecture, where layers are stacked with millimeter accuracy, flavors balanced with chemical precision, and every aspect of the product calibrated to evoke delight, bite after bite. In a world of mass production, Ferrero has mastered the art of small indulgences at scale. Each gold-wrapped sphere is a symbol of how far food science and industrial artistry can go, not just to make chocolate, but to make joy. For over a century, Hershey's has been America's chocolate. With its iconic square segments, sweet creamy flavor, and unmistakable aroma, the Hershey's milk chocolate bar has become a symbol of comfort and nostalgia. But few realize how many complex steps, both agricultural and industrial, go into creating each one of those neatly molded rectangles. From cocoa plantations to high-tech factories in Pennsylvania and beyond, the making of a Hershey's bar is a feat of logistics, chemistry, and precision food engineering. It all begins thousands of miles away from the factory floor, in the equatorial regions where cocoa trees thrive. Theobroma cacao, the tree that produces cocoa pods, is cultivated in countries like Ghana, Côte d'Ivoire, and Ecuador. Each pod contains 20 to 40 cocoa beans encased in a sweet pulp. After harvesting, farmers ferment the beans under banana leaves or in wooden boxes for several days. This natural process transforms the bitter, raw seed into a flavor precursor for chocolate, deepening its complexity. The fermented beans are then sun-dried, bagged, and shipped by container vessels to Hershey's processing facilities. Upon arrival, the beans are cleaned to remove debris and sorted by origin, size, and quality. Each origin brings its own flavor profile. Ghanaian beans offer classic cocoa depth, while Ecuadorian beans may bring floral or fruity notes. The blending of these origins is what allows Hershey's to maintain a consistent, recognizable flavor year after year. Once cleaned, the beans enter the roasting drums, massive rotating steel cylinders where they are slowly roasted at controlled temperatures. This step develops the final flavor of the chocolate, similar to roasting coffee beans. Temperature and time vary depending on bean type, but typically range between 120–160 degrees Celsius for up to 45 minutes. As the beans roast, their shells become brittle, and the internal nibs, the part used to make chocolate, develop their signature aroma. The roasted beans are passed through a winnowing machine, which cracks them open and uses airflow to separate the light, papery shells from the heavier nibs. The nibs are now ready to become chocolate. They are ground into a thick, dark brown paste known as chocolate liquor, a 100% cocoa mass that contains both cocoa solids and cocoa butter. Despite the name, there is no alcohol in this liquor, just pure ground cocoa nib. From here, the real engineering begins. The chocolate liquor is combined with milk powder, sugar, and additional cocoa butter in large mixing tanks. The exact formula is proprietary, but we know Hershey's is famous for its milk-forward flavor and slightly tangy finish. That tang is believed to come from a special milk treatment process developed by Milton Hershey himself, involving controlled lipolysis. Essentially, the development of specific flavor compounds by partially breaking down milk fats under heat. Once the ingredients are mixed into a coarse paste, the mass is sent to 5-roll refiners, large steel roller mills that gradually grind the chocolate mixture down to a particle size of roughly 20 microns. This microscopic consistency is what gives chocolate its velvety texture. If the particles are too large, the chocolate feels gritty. Too small, and it may clump or fail to release flavor properly. Each roll in the refiner is set with increasing tightness to achieve a uniform grind. After refining, the chocolate is still dry and powdery. To transform it into a smooth liquid, it enters the conch, a key piece of equipment in chocolate making. The conch is a heated, agitating chamber where the chocolate mass is kneaded for hours. This process drives off residual moisture and undesirable volatiles, improves mouthfeel, and develops the final flavor. During this stage, emulsifiers such as soy lecithin are added to improve flow properties. Once conched to specification, the chocolate is ready for tempering. This critical step aligns the fat crystals in the cocoa butter to ensure a stable, glossy, and snappy final product. Tempering involves a carefully timed series of heating and cooling cycles, typically heating the chocolate to around 45 degrees Celsius, cooling it to 27 degrees Celsius, then slightly reheating to working temperature at about 31 degrees Celsius. This allows the formation of type 5 fat crystals, which give chocolate its desirable characteristics. Now tempered, the liquid chocolate is ready for depositing. It flows into stainless steel depositors, which dispense precise volumes of chocolate into bar molds. Each mold is preheated slightly to prevent premature crystallization and is vibrated to remove air bubbles and level the chocolate surface. Once filled, the molds enter a cooling tunnel, a refrigerated chamber where the chocolate solidifies into its familiar form. After cooling, the molded bars are ejected from the molds by gentle air pressure or mechanical release. Each bar is then conveyed to a high-speed wrapping line. For the classic Hershey's milk chocolate bar, this involves two layers, an inner foil or paper liner and an outer printed sleeve. Wrapping machines fold and seal the bars at speeds of hundreds per minute, using heat sealing and cold gluing methods. Each bar is also inkjet printed with a production code for traceability and inventory control. Wrapped bars are then counted, stacked, and loaded into cartoning machines for retail multi-packs or into larger cases for warehouse distribution. Robotic arms and conveyors carry the cartons to palletizers, which arrange them onto pallets in precise patterns. Pallets are stretch-wrapped, labeled, and scanned into warehouse inventory systems. Throughout the entire process, quality control is constant and rigorous. Samples from every batch are tested for fat content, sugar ratio, particle size, flavor, aroma, and shelf stability. Sensory panels perform taste tests to ensure the product matches Hershey's official flavor profile. Microbial testing ensures food safety, and all data is logged in digital batch records to ensure traceability and compliance with food safety standards like SQF, ISO 22000, and FDA regulations. Inside the factory, automation is central. From ingredient dosing and temperature control to tank agitation and mold handling, programmable logic controllers and SCADA systems monitor every parameter. Touchscreen panels give operators live insight into flow rates, cooling curve progress, and downtime tracking. These data streams not only keep the line running smoothly, but also help predict maintenance needs and optimize energy efficiency. Another remarkable component of Hershey's production is its environmental stewardship. Modern facilities recycle water used in cooling circuits, reclaim heat from conching motors, and repurpose off-spec chocolate by reworking it into other products. The cocoa shells removed during winnowing are even used as fertilizer or animal feed, reducing waste. Supply chain transparency is also part of the modern Hershey's commitment. Cocoa beans are increasingly sourced through certified sustainable programs, with investments in farmer education and ethical labor practices. Blockchain-based platforms now allow for bean-to-bar tracking, helping ensure that every bar supports both quality and responsible sourcing. Logistically, the bars are shipped to national and international distribution centers using temperature-controlled routes when needed. Warehouses use first-in, first-out inventory systems, and retailers receive shipments in compliance with demand planning forecasts. Each bar, despite traveling thousands of miles and passing through dozens of steps, remains precisely as Hershey intended. Consistent, safe, and perfectly sweet. It's easy to take a chocolate bar for granted, to see it only as a snack or a treat. But what lies behind that silver and brown wrapper is a world-class production system that balances food science, mechanical engineering, flavor chemistry, and sustainable agriculture. From cocoa farms to Pennsylvania steel, from sugar silos to foil stampers, the making of a Hershey's bar is not just about chocolate. It's about heritage, process control, innovation, and the relentless pursuit of consistency in a product that's been enjoyed by generations. In every square, you taste more than just sugar and cocoa. You taste a supply chain running like clockwork, a formula calibrated to microns, and a commitment to quality that's lasted over 100 years. A Hershey's bar isn't just made, it's built, layer by layer, process by process, from the ground up. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step: cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids, and are now ready for the next phase: grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel where the caramel layer is firmed to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or forced chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients, glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings, are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor brix levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components: the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. The process begins with the careful selection and sourcing of raw ingredients. The primary components of KitKat bars include wheat flour, sugar, cocoa mass, cocoa butter, milk powder, vegetable oils, and emulsifiers. Nestlé, the brand behind KitKat, sources these ingredients from various regions worldwide, ensuring sustainability and adherence to strict quality standards. The cocoa used in KitKat is primarily sourced from the Nestlé Cocoa Plan, which promotes sustainable farming practices and fair trade. Once the raw materials arrive at the production facility, they undergo a series of inspections and tests to verify purity, consistency, and compliance with food safety regulations. This includes spectroscopic analysis for contaminants, moisture content testing, and sensory evaluations conducted by trained professionals. Once approved, the ingredients are stored in temperature-controlled silos and dispensing systems. The flour is kept in airtight storage to prevent contamination, while cocoa and milk powder are maintained under controlled humidity conditions to prevent clumping. Automated feeding systems transport these raw materials to the respective processing units, ensuring precise measurement and consistency in formulation. The first major step in KitKat production is wafer baking. The signature light and crispy wafer layers are created through a precise blending of wheat flour, water, sugar, and vegetable oils. Large industrial mixers, equipped with programmable logic controllers, ensure thorough mixing to produce a smooth and homogeneous batter. Once mixed, the batter is transferred via pressurized pumps to high-speed continuous wafer baking ovens. These ovens feature rotating baking plates that evenly distribute the batter across the surface, forming thin sheets of wafer. The baking plates operate at carefully controlled temperatures, typically around 180 to 200 degrees Celsius, ensuring uniform texture and color. The baked wafer sheets emerge golden brown and crisp, ready for the next stage. To enhance the crispness, the wafer sheets pass through a controlled cooling system. Conveyor belts transport the freshly baked wafers through a cooling tunnel, where calibrated fans gradually reduce the temperature to prevent thermal shock. The cooled wafers are then directed to the trimming and cutting station. Automated guillotine cutters trim the edges of the wafers to achieve uniform dimensions, ensuring consistency across all KitKat bars. Once trimmed, the wafers are transported to the layering station. Here, a fine layer of chocolate cream filling made from a precise blend of cocoa, sugar, and milk powder is evenly spread onto the wafers. Automated depositor machines ensure the filling is applied uniformly, maintaining the right thickness for optimal texture. The layering process continues with additional wafer sheets stacked on top, creating a multi-layered wafer slab. These slabs are then pressed under controlled pressure to bond the layers together without crushing the delicate structure. After layering, the wafer slabs proceed to the cutting stage. High-speed rotary or ultrasonic blade systems slice the large wafer sheets into precise rectangular portions, forming the individual KitKat fingers. Ultrasonic cutting technology is particularly effective in ensuring clean, precise cuts without generating excess crumbs or damaging the layers. The next crucial step is chocolate enrobing. The enrobing process begins with the preparation of molten milk chocolate, which is produced in large conching machines. These machines continuously grind and blend cocoa mass, cocoa butter, sugar, and milk powder, refining the mixture to achieve a smooth, velvety consistency. The conching process, which can last several hours, helps develop the rich, creamy texture and enhances the flavor profile of the chocolate. Once ready, the molten chocolate is fed into enrobing machines, where KitKat fingers pass through a curtain-like flow of chocolate. These enrobers ensure complete coverage, with excess chocolate removed using controlled air jets and vibrating conveyors. To achieve the signature glossy finish, the enrobed bars pass through a tempering unit, which carefully regulates the chocolate's crystallization process. This involves a precise cycle of heating, cooling, and reheating to stabilize the cocoa butter crystals, preventing bloom and ensuring a smooth, even texture. Following enrobing, the chocolate-covered KitKat bars enter a cooling tunnel. This tunnel, equipped with multi-zoned cooling technology, gradually reduces the temperature in stages to solidify the chocolate coating without causing cracks or condensation. The cooling process is carefully monitored using infrared sensors to maintain consistency. Once the chocolate is fully set, the KitKat bars move to the quality control and inspection stations. Advanced vision inspection systems, equipped with high-resolution cameras, scan each bar for defects, such as uneven coating, improper sizing, or misaligned layers. Bars that do not meet quality standards are automatically rejected by robotic sorting arms and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. After passing inspection, the KitKat bars are transported to high-speed wrapping machines. Individual bars are wrapped in foil or plastic film using heat-sealing technology, ensuring airtight packaging that preserves freshness. These wrapped bars are then grouped into multi-packs, which are subsequently boxed using robotic case packers. The packaging design is carefully printed with product details, barcodes, and branding elements before final sealing. The packaged KitKat bars are then palletized for distribution. Automated palletizing systems stack the boxes onto pallets in a precise arrangement to optimize space utilization during transportation. These pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for delivery to distribution centers worldwide. The logistics process is carefully coordinated to ensure timely delivery, with real-time tracking systems monitoring shipments from factory to retailer. Throughout the entire production process, extensive quality control measures are in place to uphold product integrity. Each batch undergoes rigorous laboratory testing, including microbiological screening, allergen testing, and texture analysis. Data from all processing stages is logged in automated tracking systems, allowing full traceability and compliance with food safety regulations. While the fundamental principles of KitKat production remain consistent across different manufacturing plants, regional variations may exist to cater to local tastes and preferences. For example, KitKat flavors such as matcha green tea, strawberry, and sake are produced in Japan using specialized formulations. Some factories may also incorporate alternative chocolate blends, varying cocoa content to suit market demands. Nestlé continues to innovate and optimize KitKat production through advancements in automation, sustainability initiatives, and ingredient sourcing. Modern factories are increasingly utilizing AI-driven quality control systems, energy-efficient processing equipment, and eco-friendly packaging solutions to reduce environmental impact. With continuous improvements in manufacturing technology, KitKat remains a global favorite, offering consumers a consistently delightful chocolate experience in every bite. Mars bars, one of the most iconic chocolate confections in the world, are produced in highly sophisticated manufacturing facilities designed to ensure consistency, efficiency, and quality at every step of the process. The production of Mars bars involves multiple intricate stages, from sourcing and processing raw ingredients to forming, enrobing, cooling, and packaging the final product. Each step is meticulously controlled using advanced automation technology and stringent quality control measures to ensure the signature caramel, nougat, and chocolate combination is perfectly replicated in every bar. The process begins with the careful selection of raw ingredients. The main components of a Mars bar include sugar, cocoa mass, cocoa butter, skimmed milk powder, whey powder, palm fat, glucose syrup, lactose, milk fat, and egg whites. These ingredients are sourced from trusted suppliers and undergo rigorous quality assurance checks upon arrival at the factory. Sugar, which plays a crucial role in both the nougat and caramel layers, is stored in large silos, where it is kept dry and free from contamination. Cocoa products, including cocoa mass and cocoa butter, are stored in climate-controlled environments to prevent degradation. Dairy ingredients, such as skimmed milk powder and whey powder, are tested for purity and consistency before use. Once the raw ingredients are approved, the first major stage in Mars bar production is the creation of the nougat layer. Nougat is a key structural component of the bar, providing a soft, chewy texture that contrasts with the caramel and chocolate. The nougat making process begins in large industrial mixing tanks, where a combination of sugar, glucose syrup, and water is heated to create a syrup. This syrup is then aerated using a whipping system, which incorporates fine air bubbles to achieve the desired light and fluffy texture. During this stage, egg whites or hydrolyzed soy protein are added as stabilizers to maintain the nougat's consistency. Once the nougat mixture reaches the proper texture, it is transferred onto a continuous conveyor belt, where it is spread into an even layer. This belt passes through a cooling tunnel to allow the nougat to set before it reaches the next stage of the process. The cooled nougat layer is then precisely cut into rectangular strips using high-speed guillotine cutters. These strips will form the base of each Mars bar. The next step in the process is the caramel layer. The caramel used in Mars bars is created through a controlled cooking process that involves heating sugar, glucose syrup, and milk ingredients to high temperatures. This process requires careful monitoring to achieve the perfect balance of sweetness and viscosity. Industrial batch cookers equipped with automated temperature controls ensure that the caramel reaches the ideal consistency before it is deposited onto the nougat base. The caramel is applied as a continuous sheet over the nougat layer, ensuring even distribution and uniform thickness. Once the caramel is applied, the combined nougat and caramel layers proceed through a controlled cooling tunnel, where the temperature is gradually reduced to allow the caramel to set without becoming too hard or sticky. This ensures that the layers remain cohesive and easy to cut in the next stage of production. After cooling, the layered nougat and caramel sheets are fed into an automated cutting system, which uses precision blades to slice them into individual bar-sized portions. These freshly cut bars are then transported via conveyor belts to the enrobing station, where they receive their final chocolate coating. The enrobing process is a critical step in Mars bar production, as it gives the bars their signature smooth milk chocolate exterior. The chocolate coating is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder, which is carefully tempered to achieve the perfect texture and glossy finish. The tempering process involves heating and cooling the chocolate in a controlled manner to ensure the cocoa butter crystals form a stable structure, preventing fat bloom and ensuring a smooth mouthfeel. At the enrobing station, the cut nougat and caramel bars pass through a curtain-like waterfall of molten chocolate, which fully coats them. Excess chocolate is removed using controlled air jets and vibrating conveyors to ensure an even layer without excessive buildup. Some factories use a two-stage enrobing process, where an initial thin layer of chocolate is applied as a base coat before the final, thicker chocolate layer is added. After enrobing, the chocolate-covered bars enter a multi-zone cooling tunnel, which gradually reduces their temperature in controlled stages. This cooling process allows the chocolate to set properly without developing cracks or a dull surface. The bars emerge from the cooling tunnel with a perfectly set chocolate shell, ready for the final stages of quality control and packaging. Quality control is a fundamental part of Mars bar production, ensuring that only bars meeting strict standards reach consumers. Automated vision inspection systems, equipped with high-resolution cameras, scan each bar for defects such as uneven coating, misshapen forms, or inconsistencies in size. Bars that do not meet the required specifications are automatically rejected and sent for reprocessing. Additional quality control measures include weight checks using precision weighing systems, texture analysis, and sensory evaluations conducted by trained specialists. Once the bars pass quality inspection, they proceed to the packaging area, where high-speed wrapping machines individually wrap each bar in foil or plastic film. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and placed into branded cartons, which are sealed and labeled using automated case packing systems. The final step in the process is palletization and distribution. Automated palletizing systems stack the packaged bars onto pallets in a precise arrangement to optimize space utilization during transportation. The pallets are shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retail stores and supermarkets worldwide. The entire logistics process is carefully coordinated to ensure timely delivery while maintaining the product's freshness and quality. Throughout the entire manufacturing process, Mars maintains stringent quality control and food safety standards. Each production batch undergoes extensive laboratory testing, including microbial analysis, allergen testing, and moisture content verification. The company also invests in sustainable sourcing initiatives, ensuring that key ingredients such as cocoa and palm oil are responsibly sourced to minimize environmental impact. Different Mars manufacturing facilities may incorporate slight variations in processing techniques based on regional ingredient availability, consumer preferences, or proprietary formulations. Some facilities may use alternative chocolate blends with varying cocoa content to cater to specific markets, while others may modify the nougat formulation for textural differences. Additionally, Mars continuously invests in research and development to improve efficiency, reduce energy consumption, and enhance sustainability in its production processes. With advancements in automation, AI-driven quality control systems, and eco-friendly packaging innovations, the production of Mars bars continues to evolve while maintaining the signature taste and texture that consumers have loved for generations. Twix, one of the world's most beloved chocolate bars, is manufactured using a highly sophisticated and automated process that ensures each bar maintains its signature combination of crunchy biscuit, smooth caramel, and creamy milk chocolate coating. The production of Twix bars occurs in state-of-the-art factories that utilize precision engineering, cutting-edge food processing technology, and rigorous quality control protocols. From the sourcing of raw ingredients to packaging and distribution, every step is carefully orchestrated to guarantee consistency, efficiency, and superior taste. The process begins with the selection and procurement of high-quality raw materials. The key ingredients in Twix bars include wheat flour, sugar, palm oil, cocoa butter, skimmed milk powder, cocoa mass, lactose, whey powder, salt, and emulsifiers. These ingredients are sourced from carefully vetted suppliers who must meet strict food safety and sustainability requirements. For instance, the cocoa used in Twix bars is sourced through Mars' Cocoa for Generations initiative, ensuring ethical sourcing and environmental responsibility. Similarly, the palm oil used in the biscuits and caramel is certified sustainable to reduce environmental impact. Upon arrival at the manufacturing facility, the raw ingredients undergo thorough quality checks before entering the production process. These checks include spectroscopic analysis to detect contaminants, moisture content analysis to ensure freshness, and sensory evaluations to verify taste and aroma. Ingredients that meet the necessary standards are then stored in temperature-controlled silos and storage units to maintain their quality. The first step in the actual production process is the creation of the biscuit base. Twix bars are distinguished by their crunchy, shortbread-like biscuit layer, which requires precise preparation and baking. The process begins in large industrial mixers, where wheat flour, sugar, palm oil, and leavening agents are combined to form a dough. The mixing process is carefully timed to ensure the dough reaches the ideal consistency, firm enough to hold its shape during baking, yet tender enough to create the signature crisp texture. Once the dough is fully mixed, it is transferred to an automated sheeting system. This system rolls the dough into a uniform sheet of the exact thickness required for Twix bars. The sheeted dough then moves to a rotary cutting machine, which stamps out individual biscuit fingers. Each biscuit is precisely cut to ensure uniform size and shape, allowing for seamless assembly in later stages. The cut dough pieces are placed onto conveyor belts and transported into a large industrial baking oven. These ovens operate using a continuous baking system, where the biscuit fingers travel through different heat zones that gradually bake them to perfection. The baking temperature is carefully controlled, typically ranging between 180 to 200 degrees Celsius, 356 to 392 degrees Fahrenheit, ensuring that each biscuit is evenly baked to a golden brown. Advanced infrared sensors monitor the biscuits throughout the baking process, ensuring uniformity in color, texture, and moisture content. Once fully baked, the biscuits pass through a cooling tunnel that gradually reduces their temperature, preventing cracking or breakage. Next, the caramel layer is prepared. The caramel used in Twix bars is made from a precise blend of sugar, glucose syrup, milk, and butter. This mixture is heated in large stainless steel batch cookers, where it undergoes controlled caramelization. The temperature and cooking time are crucial in achieving the perfect consistency, thick enough to stay in place on the biscuit, but soft enough to deliver a smooth, chewy texture. Once the caramel reaches the desired consistency, it is transferred to a continuous depositor system. This machine evenly dispenses a uniform layer of caramel onto each biscuit. The caramel application must be carefully controlled to ensure consistency in thickness across all bars. Any inconsistencies could lead to difficulties in chocolate enrobing or affect the final texture. With the caramel applied, the bars move along the conveyor belt to a cooling station, where they pass through a controlled cooling tunnel. This tunnel gradually reduces the temperature of the caramel, allowing it to set properly while maintaining its soft, chewy texture. After cooling, the caramel-coated biscuits are ready for the enrobing process, where they will be covered in rich milk chocolate. The enrobing process is one of the most critical steps in Twix production. The milk chocolate coating is prepared in large conching machines, which continuously grind and refine cocoa mass, cocoa butter, sugar, and milk powder. This process enhances the texture and flavor of the chocolate, ensuring a smooth, creamy consistency. The chocolate is then tempered, a controlled heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering is essential to achieving the signature glossy finish and preventing fat bloom, white streaks that can appear on improperly tempered chocolate. At the enrobing station, the caramel-topped biscuits pass through a continuous chocolate waterfall. This ensures that each bar is fully coated in an even layer of chocolate. Any excess chocolate is removed using controlled air jets and vibrating conveyors, which help distribute the chocolate evenly without excessive buildup. Some factories employ a two-stage enrobing process, where a thin base coat of chocolate is applied first to ensure better adhesion before the final, thicker chocolate layer is added. Once the bars are coated, they enter a multi-zone cooling tunnel. This tunnel is divided into different temperature zones that gradually reduce the temperature, allowing the chocolate to set perfectly without cracking or becoming dull. The bars emerge from the cooling tunnel with a firm, glossy chocolate coating, ready for the next stage of production. Quality control is a top priority at every stage of Twix production. After cooling, the bars pass through a series of automated inspection systems. High-speed vision cameras scan each bar for inconsistencies in chocolate coating, caramel distribution, and overall shape. Any bars that do not meet specifications are automatically rejected and sent for reprocessing. In addition to visual inspections, quality control teams conduct random weight checks, moisture analysis, and sensory evaluations to ensure that each batch meets Mars's stringent quality standards. Once the bars have passed inspection, they move to the packaging stage. Twix bars are individually wrapped using high-speed horizontal flow wrapping machines. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs, which are sealed in branded cartons using automated case packing systems. After packaging, the final step in the process is palletization and distribution. Robotic palletizing systems stack the packaged bars onto pallets in precise arrangements, optimizing space for transport. The pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Mars utilizes an advanced logistics network to ensure efficient delivery while maintaining product freshness. Throughout the entire production process, Mars adheres to strict food safety and sustainability standards. Each batch undergoes rigorous laboratory testing, including microbiological analysis, allergen testing, and texture verification. The company also invests in eco-friendly initiatives, such as reducing energy consumption in manufacturing and using recyclable packaging materials. Different Mars factories may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate formulations with varying cocoa content, while others may adjust the caramel consistency based on market preferences. Additionally, limited edition Twix flavors, such as Twix white chocolate and Twix peanut butter, require modifications in ingredient formulation and processing techniques. As consumer demand for innovative flavors and healthier options grows, Mars continues to invest in research and development to improve Twix production. Recent advancements in AI-driven quality control, robotic automation, and sustainable ingredient sourcing are shaping the future of Twix manufacturing. Despite these innovations, the core principles of precision, consistency, and quality remain unchanged, ensuring that every Twix bar delivers the signature, crunchy, chewy, and chocolatey experience that consumers love. The making of a Hershey's chocolate bar is a complex, highly automated process that combines tradition with cutting-edge technology. From sourcing high-quality cocoa beans to wrapping the final product, every step is optimized for efficiency, consistency, and taste. The journey of a Hershey's bar begins with the careful selection of raw ingredients sourced from around the world. Cocoa, sugar, milk, and other ingredients are carefully tested to ensure they meet the company's high standards before they are transformed into the iconic chocolate bars that have been loved for generations. At the heart of every Hershey's chocolate bar is cocoa. The company sources its cocoa beans primarily from Ghana, Côte d'Ivoire, and Ecuador, regions known for producing high-quality beans with robust flavor profiles. Cocoa farmers in these areas harvest the ripe pods, extract the cocoa beans, and allow them to ferment for several days to develop their characteristic chocolatey taste. Once dried, the beans are shipped to Hershey's production facilities, where they undergo rigorous quality checks. Each shipment is tested for moisture content, flavor consistency, and the absence of contaminants. Only the highest quality beans make it through this stringent selection process. Once approved, the cocoa beans are sent to the roasting stage. large industrial roasters expose the beans to carefully controlled heat, typically between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit, depending on the desired flavor profile. The roasting process is essential for developing the deep, complex flavors of chocolate. Different roasting profiles are used depending on whether the beans will be used for milk chocolate, dark chocolate, or other specialty products. After roasting, the cocoa beans enter the winnowing process. Specialized machinery cracks the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both the cocoa solids and cocoa butter needed for chocolate production. The nibs are then ground into a thick, dark paste known as chocolate liquor, which contains no alcohol despite its name. This chocolate liquor is the base for all Hershey's chocolate products. For Hershey's classic milk chocolate bars, chocolate liquor is combined with sugar, milk, and cocoa butter. The milk used in Hershey's chocolate is a key ingredient that gives it its distinctive taste. Unlike many European chocolates that use powdered or condensed milk, Hershey's uses fresh milk sourced from dairy farms in Pennsylvania and surrounding states. The milk is pasteurized and condensed before being blended with sugar to create a sweet, creamy base. The next stage in the process is refining. The chocolate mixture is run through a series of steel rollers that grind the particles to an ultra-fine consistency. This refining process is crucial for creating a smooth, melt-in-your-mouth texture. The finer the particles, the smoother the final chocolate will be. Once refined, the chocolate undergoes conching, a critical process that enhances flavor and texture. Conching machines, which resemble large industrial mixers, continuously stir the chocolate at controlled temperatures for several hours. This process aerates the chocolate, allowing unwanted acidic compounds to evaporate while enhancing its creamy mouthfeel. Hershey's uses a proprietary conching method that contributes to its signature flavor, which has a slightly tangy undertone due to controlled acidity in the milk. After conching, the chocolate moves to the tempering stage. Tempering is the process of heating and cooling chocolate in a precise manner to stabilize the cocoa butter crystals. Proper tempering ensures that Hershey's bars have a glossy finish, a firm snap, and a long shelf life. If the chocolate were not tempered correctly, it could develop fat bloom, a whitish streaking effect caused by unstable cocoa butter. Now, the tempered chocolate is ready for molding. Automated machines pour precise amounts of liquid chocolate into bar-shaped molds, which are then vibrated to remove air bubbles and ensure even distribution. The molds travel along a conveyor system into a cooling tunnel, where the chocolate solidifies into its final shape. Once cooled, the bars are ejected from their molds and transported via conveyor belts to the packaging area. Here, high-speed wrapping machines encase each bar in foil and branded paper sleeves, protecting the chocolate from moisture and light while ensuring a fresh, appealing presentation. Throughout the entire process, strict quality control measures are in place. High-resolution vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or size inconsistencies. Bars that do not meet specifications are automatically rejected and sent for reprocessing. Additionally, random sensory evaluations are conducted by trained taste testers to ensure that the flavor, texture, and overall quality remain consistent. Once packaged, the final step is palletization and distribution. Automated robotic arms stack the packaged bars onto pallets, which are then shrink-wrapped for stability. These pallets are loaded onto temperature-controlled trucks and shipped to retailers worldwide. Hershey's operates an advanced logistics network that ensures timely delivery while maintaining product freshness. The entire manufacturing process is designed for efficiency, consistency, and sustainability. Hershey's continues to invest in eco-friendly initiatives, such as reducing water and energy consumption in production, using ethically sourced cocoa, and optimizing packaging materials to minimize waste. Different Hershey's factories may employ slight variations in processing techniques based on regional preferences and ingredient availability. Additionally, specialty products like Hershey's cookies and cream bars or Hershey's dark chocolate require modifications in ingredient formulation and processing times. As the chocolate industry continues to evolve, Hershey's remains at the forefront of innovation, combining tradition with advanced manufacturing techniques to produce its iconic chocolate bars. Through precision engineering, strict quality control, and a commitment to excellence, Hershey's ensures that every bar delivers the same beloved taste that generations have enjoyed. The making of Toblerone, the iconic triangular chocolate bar, is a masterclass in precision engineering, premium ingredient selection, and automated manufacturing processes. Unlike conventional chocolate bars, Toblerone stands out for its distinctive shape, rich Swiss milk chocolate, and the inclusion of honey and almond nougat. Every step, from sourcing the finest ingredients to molding the signature peaks, is meticulously controlled to ensure quality, consistency, and adherence to the Swiss chocolate making tradition. The process begins with sourcing high-quality ingredients. Toblerone's signature flavor comes from its carefully selected components: Swiss milk, sugar, cocoa mass, cocoa butter, honey, almonds, and egg whites. The milk, sourced from Swiss dairy farms, is a critical ingredient that contributes to the creamy texture. The cocoa is sourced from sustainable farms in Ghana and Ecuador, where beans are hand-harvested, fermented, and dried under strict quality control measures. Almonds are procured from select suppliers, ensuring they meet the required standards of size, flavor, and crunch. The honey, a key component that adds a subtle sweetness, is sourced from European beekeepers specializing in high-quality aromatic varieties. Once the ingredients arrive at the production facility, they undergo rigorous quality checks. Advanced spectroscopic analysis, moisture content testing, and flavor profiling ensure that each ingredient meets the brand's high standards. The cocoa beans are then roasted at carefully controlled temperatures to develop their deep, complex flavor. Different roasting profiles are used depending on whether the beans will be used for Toblerone's milk, dark, or white chocolate variations. After roasting, the cocoa beans move to the winnowing stage, where high-powered machinery cracks them open and removes the husks. The remaining cocoa nibs, which contain the essence of the chocolate, are then finely ground into a thick, rich paste known as chocolate liquor. This forms the base of Toblerone's chocolate. The chocolate liquor is blended with sugar, cocoa butter, and Swiss milk powder to create the signature, smooth and creamy chocolate mixture. The next step in the process is refining. The chocolate mixture passes through a series of heavy-duty steel rollers that break down the particles to an ultra-fine consistency. This is crucial in achieving the signature melt-in-your-mouth texture. The refining process also helps blend the ingredients evenly, ensuring a perfectly smooth mixture. Following refining, the chocolate undergoes conching, a process that enhances its texture and flavor. Large conching machines continuously mix, aerate, and heat the chocolate for several hours, allowing volatile acids to evaporate and the flavors to develop fully. Toblerone's conching process is fine-tuned to create a silky texture and a well-rounded, rich taste. Meanwhile, the honey and almond nougat mixture is prepared in a separate area of the factory. Sugar, honey, and egg whites are heated and aerated to create a light, chewy nougat. Almonds, which have been roasted to bring out their nutty aroma, are chopped into small pieces and folded into the nougat mixture. The nougat is then cooled and ground into fine pieces before being incorporated into the chocolate. Once the chocolate has completed the conching process, the finely ground nougat mixture is carefully folded into it, ensuring even distribution. This step is crucial in maintaining the signature texture and taste of Toblerone. With the chocolate and nougat mixture fully blended, the next stage is tempering. Tempering is a precise process of heating and cooling chocolate in a controlled manner to stabilize the cocoa butter crystals. Proper tempering ensures that the chocolate has a glossy finish, a firm snap, and a smooth texture. Toblerone's tempering process is carefully calibrated to achieve the ideal consistency before molding. Molding is where Toblerone's iconic shape comes to life. The tempered chocolate is poured into custom-designed triangular molds that give the bar its distinctive peaks. The molds are gently vibrated to remove air bubbles and ensure even distribution of the chocolate. After molding, the bars pass through a cooling tunnel where they are gradually cooled to allow the chocolate to set perfectly without cracks or imperfections. Once solidified, the bars are removed from the molds and transported to the quality control station. Each bar is inspected using high-resolution vision cameras, which detect any inconsistencies in shape, texture, or coating. Automated sorting systems remove any defective bars, ensuring that only perfectly shaped Toblerone bars proceed to packaging. The packaging process is designed to maintain the freshness and integrity of the chocolate. Toblerone bars are individually wrapped in foil to protect them from moisture and light, then placed into the iconic triangular cardboard cartons. High-speed packaging machines fold and seal the cartons with precision, ensuring that the bars remain securely enclosed. Following packaging, the bars are palletized using robotic systems, stacked carefully for stability during transport. These pallets are shrink-wrapped and loaded onto trucks for distribution to markets around the world. Temperature-controlled logistics ensure that the chocolate remains in perfect condition during transit. Throughout the entire manufacturing process, Toblerone maintains strict quality control measures. Each batch undergoes laboratory testing, including texture analysis, microbial screening, and taste assessments conducted by trained specialists. Data is continuously logged in automated tracking systems, allowing for full traceability of every Toblerone bar produced. Different Toblerone manufacturing facilities may employ slight variations in processing techniques depending on regional ingredient availability and market preferences. Specialty additions, such as Toblerone white chocolate or Toblerone dark, require slight modifications in ingredient formulations and processing steps. As consumer preferences evolve, Toblerone continues to innovate while maintaining the brand's heritage of Swiss chocolate craftsmanship. Investments in sustainable cocoa sourcing, eco-friendly packaging solutions, and advanced automation ensure that Toblerone remains a global favorite while reducing its environmental footprint. Through precision engineering, time-honored techniques, and a commitment to quality, every Toblerone bar delivers the signature taste and texture that chocolate lovers around the world cherish. The production of Snickers, one of the world's most popular chocolate bars, is a highly automated and meticulously controlled process designed for efficiency, consistency, and large-scale output. With its signature combination of nougat, caramel, peanuts, and milk chocolate, Snickers is produced in state-of-the-art facilities that use cutting-edge food processing technology, ensuring that every bar meets the brand's high-quality standards. From sourcing the finest raw ingredients to packaging and distribution, every step is optimized to deliver the same taste, texture, and satisfaction in every bite. The journey of a Snickers bar begins with the careful selection of raw materials. The main components include sugar, peanuts, milk powder, cocoa mass, cocoa butter, palm oil, glucose syrup, egg whites, and emulsifiers. These ingredients are sourced from carefully vetted suppliers, ensuring compliance with strict food safety and sustainability standards. Mars, the company behind Snickers, prioritizes responsible ingredient sourcing, ensuring that cocoa is ethically obtained through its Cocoa for Generations program, which promotes fair labor practices and sustainable farming methods. Peanuts, another crucial ingredient, are primarily sourced from the United States, where they are grown under controlled conditions to maintain size, flavor, and crunch. Once the ingredients arrive at the manufacturing facility, they undergo a rigorous quality control process. Each batch is tested for moisture content, purity, and potential contaminants. Peanuts, in particular, go through an additional inspection phase, where they are sorted by size and quality. High-speed optical sorting machines remove any defective or discolored peanuts, ensuring that only the best nuts make it into Snickers bars. The first major step in the Snickers production process is creating the nougat base. Nougat provides the chewy texture that forms the foundation of the bar. It is made by combining sugar, corn syrup, and water, which are heated in large industrial cooking vats to create a syrup. This syrup is then aerated using high-powered whipping machines, which incorporate fine air bubbles, giving the nougat its characteristic light and chewy texture. Egg whites or soy protein are added as stabilizers to help maintain consistency. Once aerated, the nougat is spread onto a moving conveyor belt in a continuous sheet, where it is allowed to cool and set. This process is carefully controlled to prevent the nougat from becoming too hard or too soft. Automated guillotine cutters then slice the nougat sheet into uniform rectangular portions, ensuring that each piece is the exact size required for Snickers bars. Next comes the caramel layer. The caramel in Snickers is made from a blend of sugar, glucose syrup, milk, and butter, which is heated in large stainless steel batch cookers. The temperature is carefully monitored to achieve the perfect viscosity, thick enough to hold its shape, but soft enough to provide a smooth, chewy texture. Once cooked to perfection, the caramel is poured in a controlled stream onto the nougat base. The caramel-covered nougat passes through a cooling tunnel, where it sets just enough to be firm, but still pliable. Now it's time to add the peanuts. Before being incorporated into the bars, the peanuts are roasted in industrial ovens to enhance their flavor and crunch. After roasting, they are cooled and evenly distributed over the caramel layer using precision peanut dispensers. These machines ensure that each bar receives the right amount of peanuts, maintaining uniformity across all Snickers bars. Once the peanuts are in place, the layered nougat, caramel, and peanut sheet moves to the cutting stage. High-speed rotary blades slice the continuous sheet into individual bar-sized portions. Each cut must be precise, ensuring that the caramel and nougat layers remain intact while maintaining a consistent size. The next critical step is chocolate enrobing. The milk chocolate coating used for Snickers bars is made from a blend of cocoa mass, cocoa butter, sugar, and milk powder. This mixture is refined and conched in large machines that continuously grind the chocolate to achieve a smooth texture. The chocolate is then tempered, a process that involves controlled heating and cooling to stabilize the cocoa butter crystals. Proper tempering ensures a glossy finish and prevents fat bloom, which can cause chocolate to develop a dull appearance. At the enrobing station, the cut bars pass through a waterfall of liquid milk chocolate, fully coating them. Excess chocolate is removed using controlled air jets and vibrating conveyors, ensuring an even layer without excessive buildup. Some factories use a two-stage enrobing process, where a thin base coat of chocolate is applied first to create a stable foundation before the final. Thicker chocolate layer is added. After enrobing, the bars enter a multi-zone cooling tunnel. This tunnel gradually lowers the temperature in controlled stages, allowing the chocolate to set properly without developing cracks or dull spots. Once fully cooled, the Snickers bars emerge with a perfectly solidified chocolate coating, ready for quality inspection. Quality control is a critical component of Snickers production. Each bar undergoes a series of automated inspections to ensure that it meets strict specifications. High-speed vision inspection systems equipped with high-resolution cameras scan each bar for defects such as uneven coating, improper size, or misshapen layers. Any bars that do not meet the required standards are automatically rejected and sent for reprocessing. Additional quality checks include weight verification, moisture content analysis, and sensory testing conducted by trained specialists. Once the bars have passed inspection, they move to the packaging stage. Snickers bars are individually wrapped in plastic film using high-speed horizontal flow wrapping machines. These machines use heat sealing technology to create airtight packaging that preserves freshness and prevents contamination. The wrapped bars are then grouped into multi-packs and packed into branded cartons using automated case packers. The final step in the process is palletization and distribution. Automated systems stack the packaged cartons onto pallets in precise formations, optimizing space for transport. These pallets are then shrink-wrapped for stability and loaded onto temperature-controlled trucks for distribution to retailers worldwide. Snickers bars are shipped to over 70 countries, requiring an advanced logistics network to ensure that they arrive fresh and in perfect condition. Throughout the entire production process, Mars maintains stringent food safety and sustainability practices. Each batch undergoes extensive laboratory testing, including microbiological screening, allergen testing, and texture verification. The company also invests in sustainable ingredient sourcing, reducing its environmental footprint through energy-efficient manufacturing processes and eco-friendly packaging solutions. Different Snickers manufacturing facilities may employ slight variations in processing techniques based on regional ingredient availability and consumer preferences. For example, some regions may use alternative chocolate blends with varying cocoa content, while others may modify the nougat or caramel consistency based on market demands. Additionally, special edition Snickers bars, such as Snickers almond or Snickers peanut butter, require modifications in ingredient formulation and production methods. As consumer preferences evolve, Mars continues to innovate while maintaining the classic Snickers taste and texture. Advancements in automation, AI-driven quality control, and sustainable manufacturing practices are shaping the future of Snickers production. Despite these innovations, the fundamental principles of precision, consistency, and quality remain unchanged, ensuring that every Snickers bar delivers the same delicious combination of chewy nougat, gooey caramel, crunchy peanuts, and smooth milk chocolate that has made it a favorite among chocolate lovers worldwide. The production of Tony's Chocolonely chocolate bars is a carefully designed process that emphasizes ethical sourcing, sustainability, and high-quality chocolate-making techniques. Unlike traditional chocolate brands, Tony's Chocolonely is dedicated to creating a slave-free chocolate industry, ensuring that every step in the supply chain is transparent and fair. From sourcing cocoa beans from cooperatives in West Africa to molding and packaging the final bars, the production process is a seamless blend of traditional craftsmanship and modern automation. The journey of a Tony's Chocolonely bar begins with cocoa sourcing. The company partners with cooperatives in Ghana and Côte d'Ivoire, regions that are known for cocoa production, but also face significant challenges related to child labor and unfair wages. Tony's Chocolonely implements direct trade practices, paying a premium for cocoa and providing additional support to farmers through training programs and financial resources. This ensures that the beans are ethically sourced while maintaining a high standard of quality. Once harvested, the cocoa beans go through a meticulous post-harvest process. Farmers ferment the beans for several days, a crucial step that develops the deep, complex flavors needed for premium chocolate. After fermentation, the beans are spread out under the sun to dry, reducing moisture content and preventing mold growth. When dried to the appropriate level, the beans are packed into jute sacks and shipped to Tony's Chocolonely's processing facilities. Upon arrival at the factory, the beans undergo rigorous quality control checks. Samples from each shipment are tested for moisture levels, flavor consistency, and potential contaminants. Beans that pass inspection are stored in climate-controlled silos to maintain freshness before entering the production line. The first step in the chocolate-making process is roasting. Large industrial roasting machines heat the beans at precise temperatures, usually between 120 to 150 degrees Celsius, 248 to 302 degrees Fahrenheit. This process enhances the natural chocolate flavors and eliminates unwanted bitterness. The roasting time and temperature depend on the type of chocolate being produced. Dark chocolate requires a slightly longer roasting process than milk chocolate to develop its rich, bold flavors. Once roasted, the beans enter the winnowing process. A specialized machine cracks open the roasted beans and removes the outer husks, leaving behind the valuable cocoa nibs. These nibs contain both cocoa solids and cocoa butter, the essential components of chocolate. The nibs are then ground into a thick, smooth paste known as chocolate liquor. This process, carried out by industrial grinders, reduces the particle size of the nibs, creating a velvety consistency. At this stage, different chocolate variations begin to take shape. For Tony's Chocolonely's milk chocolate bars, the chocolate liquor is combined with sugar, milk powder, and additional cocoa butter to create a creamy texture. For dark chocolate, higher cocoa percentages are used with less sugar and no milk. The next step in the process is refining. The chocolate mixture is passed through heavy-duty steel rollers that grind the ingredients into ultra-fine particles. This step is crucial for achieving the smooth texture that defines high-quality chocolate. The finer the particles, the better the melt-in-your-mouth experience. Following refining, the chocolate undergoes conching, a process that enhances both texture and flavor. Large conching machines continuously mix and aerate the chocolate for several hours, allowing any residual acidity to evaporate while intensifying the chocolate's richness. The conching time varies depending on the desired flavor profile. Longer conching results in a smoother, more developed taste. After conching, the chocolate is tempered, a precise heating and cooling process that stabilizes the cocoa butter crystals. Proper tempering ensures that Tony's Chocolonely bars have a glossy finish, a satisfying snap when broken, and a long shelf life without developing fat bloom, the white streaks that can appear on improperly tempered chocolate. Once tempered, the liquid chocolate is ready for molding. Unlike most chocolate bars, Tony's Chocolonely bars are intentionally molded in an uneven pattern, symbolizing the unequal distribution of wealth in the chocolate industry. Automated machines pour precise amounts of chocolate into these custom-designed molds, which are then gently vibrated to remove air bubbles and ensure even distribution. The molds are then transferred to a cooling tunnel, where the chocolate gradually solidifies under controlled temperatures. This process prevents the bars from developing surface defects and ensures that they retain their perfect shape. Once the chocolate has fully set, the bars are ejected from the molds and sent to the quality control station. High-speed vision inspection systems scan each bar for defects, such as air bubbles, improper molding, or uneven texture. Any bars that do not meet the required standards are removed from the production line and either reprocessed or discarded. After passing quality checks, the bars move to the packaging stage. Tony's Chocolonely uses brightly colored, easily recognizable wrappers, each featuring bold typography and branding. The packaging process is fully automated, with high-speed wrapping machines, sealing each bar in foil and paper to protect it from moisture and contamination. The wrapped bars are then packed into cartons using robotic case packers. The final step in the process is palletization and distribution. Automated robotic systems stack the packaged bars onto pallets in a precise arrangement, optimizing space for transport. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars' internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate-controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the Brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber, where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars' proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms or high-speed diverters organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data, embedded in barcodes or RFID tags, about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes, without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars Global Standardization Team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat.